So for our sixth and final video coming up, we're going to need an intermediate subroutine, and that is our ability to compute the tangent to an arbitrary point on an ellipse, which is one of the 5 points that were originally used to define it. So the original 5 points were A, B, C, D, E, right? And we saw in the very first video that if 6 points lie on a conic, and let's just assume that F was not given, but I'm going to use this as an auxiliary point, and I'm going to imagine to be on the conic. So if we're given these 6 points, we'd get these 3 intersections that would be collinear on this Pascal red line. Okay. Now, what I want you to see here is that I've asked GeoGebra to actually draw, using its own internal method, a tangent line. Let's make this tangent line be magenta. Okay. This tangent line here at point A to the conic. Now, of course, I don't have that capability in the kind of constructions that I'm making, but I want you to just take note of the fact that if this imaginary point F, okay, is made to come arbitrarily close to point A, okay, the chord AF becomes closer and closer to what the tangent at A is. You can see that, right? Likewise, if I move F close to E, the chord EF becomes closer and closer to the tangent to the conic at E. But let's actually focus on A here. And I want you to see that there's a very simple way to calculate the line that is precisely tangent to the conic at A, just by looking at what's happening to Pascal here. So let's look precisely what's happening to Pascal. This first spot here is the intersection of AB with DE, which does not depend on F. So you can see here that as I move F, this first intersection here, let's give this guy a name, for example, G. It does not depend on the position of F. Okay? Now, the other 2 intersections do depend on the position of F. Let's call this guy here whatever GeoGebra wants to call it. Let's call this guy here H, and let's call this one here I. Okay? So as I move F around, these 2 intersections do depend on the position of F. But in particular, when F is approaching A, okay, and that line AF approaches the desired tangent, okay, look at what happens. Let's assume now that F is ever so close to A, and we could even say F is A. Okay, now let's look at what happens. Did we miss? We're now going to get H to be the intersection of CB or BC with EF or EA. So we can compute point H when F tends to A. Point G was computed all along, it doesn't move. So now I have this Pascal line, this virtual Pascal line in the limit, which connects EA through H with GH, these 2 given points here. Okay, so I can extend this line, and look at what's happening to this red line, okay, in particular, how it's going to intersect the CD line at this desired point. So let's go ahead and make this guy come pretty close to A, so that I'm very close to the tangent. And now maybe I can nudge this so that the intersection can come closer to us. Let's see here. Let's see if I can bring that intersection closer to us. This one over here. Yes. So the intersection of line HG with F on top of A with line CD. Now when F is exactly on A, okay, right there, and I did this manually, you can see here that the red line from HG passes through this point I, okay, just as the tangent through A passes through the point I. So a very easy way for me to construct this tangent is to simply say, I'm going to delete the tangent that GeoGebra inserted for me, and I'm going to assume that F is on top of A, and my tangent is simply going to be the intersection of lines CD with HG, and again everything is very well defined, And I'm going to just draw this line. I'm going to take point I, and I'm going to connect it to F. Okay? But F doesn't exist, right? So if F doesn't exist, okay, if F doesn't exist, all I've got here is what you see on the screen now. I've got, in fact, a pentagon, A, B, C, D, E, okay, and I'm just drawing the following lines. I'm drawing CB meeting EA at H. This is pretty well defined. Then I'm drawing DE and meeting BA at G. Okay, and I'm drawing this virtual Pascal line. Okay, and I'm making it intersect the missing side CD at I. And I'm just taking I and drawing a line through A. And when I do that, I know that that line, which I'm going to color here as green, is in fact the tangent line that we seek. Okay? So this is a very interesting construction, and behind it there is this limit concept, right? That there is an F vertex that I've moved infinitesimally close to an infinitesimal distance of A, and in the limit you get this pentagon construction that returns to me this thing here. So what we're going to need in the next video is the following. I'm going to basically refer to this construction saying find the tangent at a particular point in the next construction, and we're just going to assume that we used this particular algorithm to get to the tangent, and notice that this algorithm is not in any way using the shape of the ellipse itself. It's only using 5 given points. So you don't even know what the ellipse looks like, but you're saying if I knew what it looked like, the tangent to it at this particular point on it is given by this green line. And that's all I need. Okay, so let's restore here the conic. And just to remind ourselves, okay, we already know how to locate the center of the conic. We already know how to locate the axes. So now we know how to locate a tangent, and the next step will be how do we use these 3 bits of information to locate the vertices and the foci of the ellipse. So I'll see you on the next video.